Yeah, so I'm saying that last week, last week, was it Friday? We looked at frictional forces. We looked at the case of a car negotiating a corner, and we looked at the forces that are at play. We said we'll have friction force between the tires and the tarmac or the road. We'll also have the friction, the force, centripetal. The centripetal force, which is trying to push the car outward. If the car is trying to negotiate a corner like that, we say that centripetal force will be always perpendicular to the motion of the object. So the motion, if the car is going in that direction, centripetal force will be going in that direction, will be pointing that direction. And we also looked at these other forces, which we resolved in the x-axis. Starting with the y-axis, we came up with a pretty good equation, which this equation is also important if you just memorize it. Sometimes they'll ask you to say, what is the friction between the tires and the car and the tarmac when the car is trying to negotiate a certain road, a certain corner. They may ask you for the friction force, just like that, just asking you, say, what is the friction force between the tires and the road for a car trying to negotiate a certain curve or a certain corner with such and such velocity. Or they may even ask you for the velocity, or depending on whatever. Sometimes this formula is very handy, but the good thing is you know where it comes from. So even if you don't need, most definitely, I wouldn't even encourage you to master this formula. I would just encourage you to always you sum your forces in the y-axis, and then you also sum your forces in the x-axis. Sorry, this is x. It is always a good thing to do that. Sum forces in the y-axis, you get to know what your normal force is, and then from there you can use the normal force. The normal force, given that friction force is equals to mu normal. So once you get your normal, it's very easy for you to get your friction force. Always get the expression for your normal force first, all right? Because it is always going to be useful in your calculation of friction force. So we went further and looked at the situation of a banked rod. In fact, this one was not supposed to be mg sine theta. This was supposed to be normal sine theta. And of course, friction force might be there, but on a banked rod, on a road with a rod, this is a rod. This rod is like curving like this. I can't show how it is curving. I've just shown portion of it. But on a road which is called banked rod, I'm sure you can see what here we have marked, banked rod. We don't usually consider friction force. So we only look at when we draw our Cartesian plane like this. Actually here, it's mostly convenient to draw our Cartesian plane just like that, the way we normally would draw our Cartesian plane, as this one as our x-axis and that one as our y-axis. And then from here we see that our normal force is at an angle. We can of course compute the normal force in the y-axis and in the x-axis. Actually, I think I sent you a good diagram where I had changed a few things and just showed you that when you are resolving, of course, forces, when you have drawn your Cartesian plane properly like this, of course, you know that there are instances where you may find it convenient for you to rotate your Cartesian plane as well, like that, with this being your x-axis and that being your y-axis. That is usually, this case is usually convenient when you are solving, forces, when you are solving forces on an inclined plane, when you are solving forces on an inclined plane, yeah, inclined plane, like that. So there are certain instances which are convenient for you to rotate your Cartesian plane. For example, if you have maybe a box which is sliding over an inclined plane given a certain angle. Yeah, I know we looked at it, but just a recap. So here in this case, when we are looking at an inclined plane, we are trying to see the forces going down and the forces coming up and the like. It is best if we rotate our axis to accommodate this. I mean, to just help us analyze forces on this inclined plane. But in a case where we are talking about circular motion, when we are talking about circular motion, especially on a banked road, when we deal with motion around in a circle of a certain radius on a banked road, it is always necessary to maintain our Cartesian plane upright, like this, upright, so that we can resolve our forces normally the way we would resolve them. Our weight always pointing downward, and then here we'll have our normal force. We'll have our normal force at an angle, and then of course we can resolve our normal force in the x-axis and also in the y-axis. So here we'll have x component of the normal force, and then here we'll have wow, that's good singing, eh? Simbarasha, is it you singing?
No, it was just someone else singing.
Oh, they are talented actually. You should congratulate them.
But you're very talented. And thank you, sir.
Okay. Good to have you, Mr. Simbarashe. I hope you'll be able to follow. We're just having a quick recap on what we learned so that we can start solving equations. Good to have you.
All right. Thank you.
Okay, so yeah, it is good. You know, one thing that I appreciate very much is the fact that we did a quick recap on trigonometry. We did a quick recap when we were looking at vectors. We looked a bit at trigonometry so that you know when to use the cosine function and the sine function, because there's a myth that is there that cosine function is only used in the x-axis and sine function is only used in the y-axis. But we saw that, as you can see even here on the next slide, we see that in the y-axis, actually, in the y-axis, for our normal force, we used cos. Why did we use cos? Is because if our normal force is given at this angle here, and this angle is given with respect to the y-axis, all right? This angle is given with respect to the y-axis, meaning if I draw, what does it mean? It means that my y-axis is adjacent to this angle. Using trigonometry, we know that my y-axis is adjacent to this angle. So if I want to find the y component of the normal force, and this normal force is pointing upward in that way, all right, upward in that way. Again, I'll also show you that the aspect of negative angles and positive angles in a bit. But here, as you can see, the normal force, if something is pointing in a direction like this, we know that its component in the y-axis will be positive, but its component in the x-axis will be negative. I'm sure you know that if something is pointing like this. So that's how come when we go to the next slide, we see that our normal force is given positive, all right, and our weight is given negative. Our normal force is given positive, our weight is given negative. Weight, why is weight negative? Weight, as you can see, mg is pointing in the negative y-axis. So when we sum forces in the y-axis, we see that since normal force was pointing that direction, we know that its component in the y-axis would be positive. Of course, that is why we have n cos theta in the y-axis. And we have shown that because the angle was taken here, we saw that the y-axis is adjacent to the angle. No wonder we are using the cosine function. So we came up with an expression of normal force like this. And then also in the x-axis, we showed that in the x-axis, we'll have the normal force pointing in the negative x-axis. But just like at this point, remember even here when we were dealing with this type of motion on a level field, on a ground, we showed that centripetal force is always pointing towards the positive x-axis. So even here, it will still point towards the positive x-axis, all right? Because if an object is moving like this, even if it is on a banked road, centripetal force will always be away from the circumference of that circular path. And in this case, it is actually in the x-axis, positive x-axis. Are we together? Are we following?
May I have some clarity in what you just said? You said the centripetal force is always in the positive x-axis, away from the circumference of the circular path. Can you please explain?
Okay. It's only that I am away from the light. I'm not sitting in a position where there's good lighting, but I would have turned on my video so that you see my fingers and I do a bit of some explanation. But what I mean is, if a vehicle or any object, even yourself, if you try, have you ever, let me ask you a question. Have you ever picked a baby and then you hold them by the hands and you start swinging? You start swinging the baby around like that. You hold, I don't know how I can draw it. You are like this. I don't know if that's how you look like, but no, I don't think so. Anyway, so you are like this. You are holding a baby. I don't know if I'm going to. I don't know if this is how a baby looks like, but you start swinging around in a circular path. How do you feel? Do you feel like the baby is moving away from you or the baby is moving towards you when you are swinging in that path? Do you feel like the baby is moving towards you or the baby is moving away from you? If you let go of the baby, what do you think will happen? Will the baby swing towards you, or the baby will spiral away from you?
Away from me.
So if the baby will move away from you, meaning as you are rotating that baby in that circular path, there is a centripetal force which is pushing the baby away from you, so that when you let go of the baby, your force, which you are counteracting the centripetal force, has been broken. So the centripetal force will take over and push the baby away from you. So even a car navigating a certain corner, it will always, centripetal force will always try and push the car away from the center of the corner. So if the center of the corner is here, the centripetal force will not push the car towards the corner. It will always, towards the center, it will always try to push the car away from the center of the center of the corner of that circular path. Is that okay?
I thought the centripetal force would be the one that like pulls the car towards the corner, and then the I don't know. I can say the tangential force, or I don't know, the linear velocity will be the one going in the other direction. So when the centripetal force is cut off, that's why the body will fly perpendicularly to the path it was going around in. So I don't.
Okay. Now, there is no force or whatsoever that pushes. There's no force that pushes. You remember we have planet Earth here, right? And the sun is right here. Planet Earth is always moving in that circular path. Why does it move in that circular path? It is because of gravitational pull. The sun is pulling the earth with a force of gravity. All right. Sometimes it may be a force of gravity. Sometimes it may be a tension. In the case, for example, if you have a circular path and the body is moving in that circular path, and then you have this is the oasis, the center, and you have some string or some cord or some sort, you have tension force trying to pull the body towards the center, but centripetal force will always be taking the body away. No wonder centripetal force is given by a formula, is given by this formula, mv squared over r. So due to the changing of the velocity, due to the always changing of the velocity, all right, if the velocity is pointing in that direction at an instant, meaning centripetal force is in that direction. So centripetal force will always be trying to pull or to push away from the center of the circle. There is no, if we don't have gravity or any tension or any string or any connection between the center and the path and the oasis and the object, this object will obviously just be lost away from this circle. It will fly away, it will go away. So centripetal force is not what pushes inward, it is what pushes outward from that circular path.
Okay, it makes sense now.
Awesome. Simbarasha, you have a question?
Yes, sir. So from that, can we conclude to say that acceleration, centripetal acceleration is the one that is center seeking, then the force is the one that's going outside there?
In fact, that same centripetal acceleration, do you know that the direction of acceleration follows the direction of the force? Do you know that, Simbarasha, do you know that the direction of acceleration follows the direction of force? Do you know that?
I heard it followed the center.
Did you read, or you are assuming? Did you read somewhere also?
Yeah, I think I read somewhere also.
I guess it could be centrifugal, because there's also a force called centrifugal. Try and research on that. But if centripetal force is pointing in that direction, for example, in the positive x direction, that means that centripetal acceleration is also pointing towards the same point, towards the positive x-axis. Let me give you an example of gravitational force. Remember, force of gravity is always pointing in the negative y-axis. What is the sign of acceleration due to gravity? What is the sign of acceleration due to gravity, Simbarasha?
The sign of acceleration due to gravity, G.
what's the sign? Sign, is it a positive or negative? Sign is positive.
Negative. Negative.
It's negative because a force of gravity is negative. So the negative 9.8 comes from the negative force of gravity. So if like the way you are saying, centripetal acceleration is always towards the center, then it would mean that centripetal acceleration and centripetal force will have opposite signs, and that can't be the case. We can't have centripetal acceleration pointing this way and centripetal force pointing that way. That would be defiance of physical laws that we know. We know that the force, the direction of the force will be the direction of the acceleration. So if the direction of the force is pointing us outward, then the direction of the acceleration will always also point us outward. Is that okay?
Yes, sir.
In fact, I'm sure you heard the explanation with the experiment I gave Kawama. I gave an explanation for Kawama to say, when you are swinging a baby around a circular path, where do you feel? You can even feel it, because physics is physical. You can actually detect it. It's not like mathematics where you just have some construct in your head. But physics, you can actually detect it, and you can see that if I'm swinging a baby around a circle, I'll always feel like the baby is trying to move away from me, such that if I let go of the baby will swing away from me. All right. Why is the baby swinging away from me? It's because of centripetal acceleration. And centripetal acceleration is taking the baby away. That is also, in fact, it is because of centripetal force. And that baby will move because of that centripetal force. The baby will be pushed away. So I hope we are clear on that. We just wanted to have a recap. In fact, let me just put water in the pot. You know, I'm also the woman of the house, so a bit, 1 minute. Okay, are we still there?
Yes, we are.
Yes, sir.
Awesome, awesome. So, mind you, imagine your tutor cooks, and when I'm stirring in the pot, I'm applying centripetal what? Who can know that? Who can determine that? When I'm stirring the when I'm stirring the spoon in the pot, what force am I applying?
Centripetal force.
Okay, that was just a light moment. So we have shown a few things where the forces are, and we have shown what our normal force is, and we have also shown that in the x-axis we have centripetal force minus our normal force. What is our normal force in the x-axis? Our normal force in the x-axis, given this angle here where it is, this angle here, it means that our normal force will be n sine theta, all right? And everything should be balanced so that the vehicle doesn't spiral out. So no wonder we have a 0. So when we take n sine theta on the other side, we have this expression, and this expression we can replace where there's our n, we can replace it with this expression that we had found here, which is mg over cos theta, and then this sine theta is exactly what we have there. And when we do the manipulations, we have mg tan theta. From there, we can even manipulate further to cancel out the m's and introducing acceleration. We know that acceleration is equals to force over m, and this is the force that we found over m. We get a good equation here. If you want to know the acceleration, centripetal acceleration, you know acceleration due to gravity, just know the angle. Which angle are we talking about? This angle. If you know this angle, you know acceleration due to gravity, you can know your centripetal force by just computing g tan theta, all right? And then, of course, you can also, if you want to also know your velocity, you can also use this expression. So let's look at an example so that we don't waste so much time with the same thing that we looked at last time. So let us have, let us have Tekla to read for us this question.
All right. It reads, a train is traveling at 50 kilometers per hour on a curve, the radius of which is 500 meters. If the distance between the rails is 1.5 meters, find how much the outer rail must be raised above the inner so that there may be no lateral thrust on the rails.
Awesome. So, have we understood the question? What are we getting from the question?
I think because they're asking for the angle at which the rails are raised, they've been banked.
They have been banked. Awesome. Anyone else? I heard someone else also wanted to attempt. Okay, so we have a situation whereby, I tried to attempt to draw, but my art was very poor in grade 1. In fact, I got a 0 in art in grade 1. That is, if we even had art in grade 1. So we have a situation whereby a train, in fact, even before I explain further, I would also want to mention one thing that I mentioned earlier on, is that certain questions, the way they are going to come, they are going to assume you have seen a train before. Me, I come from Northwestern, where we just, some people don't even know what a train is. In Northwestern, we have never, in fact, imagine how big I am. I've never been in a train, all right? So some of our friends from Southern Province can laugh at me, or from, which one is this? So the Southern Province, okay, from Southern Province can laugh at me because probably they have been in a train before. So, but again, as at the university, they would assume that you are very learned to an extent whereby you know about these basic things of life. You know about a train, and you know about the rails of a train. If you have a train track like this, we know that we have the rails, right? One rail and the other rail. They are usually connected by some, maybe planks or whatever, but there are these things that are always moving across the railway. But the rails are these. We know that these are the rails, right? This one, the outer rail, the inner rail. We know these are the rails, right? Are we together?
Yes.
Yes.
Now suppose,
Yes,
awesome. Now suppose we are in a circular path. This rail is moving in a circular path like this, all right? Inner rail and outer rail. So we have our rails being connected like that. So I always tell you, friends of mine, to be using even a bit of, should I call it common sense, to just imagine some of these things. So they are assuming that this path has a certain radius, all right? R, all right? It has a certain radius. So the train is negotiating this corner. But now, if the train is moving at a high speed, because of centripetal force, there will be some thrust on the rails. In fact, the rails can even be destroyed if the train is moving at a very high speed in trying to negotiate this path. These trains, these rails, or on a long run, they'll be destroyed. So what do? They bank them. They put them at a certain angle. So you can't see, here you can't really see these rails like this, but let me just assume we have banked them at an angle like that. So we have the outer rail, all right, or the inner rail is like that, and the outer rail is like that, all right? So the train is moving on this railway, all right? So now we have been even given, what? The distance between this rail and that rail. What is the distance between one rail and the other? It is 1.5
5 meters.
Awesome. So when we bank the railway, it means that we have raised one part of the rail, not so. One part of the rail, we have kept it on the ground, but the other part, we have raised it by a certain height, h. We have raised it by a certain height, h. All right, they want to find how much the outer rail must be raised above the inner rail. All right, so we want to find out how much this outer rail has been raised. Of course, we can do that first by finding this angle, and then using trigonometry, we have the hypotenuse and the opposite, we can find this height. All right, so find out how much the outer rail must be raised above the inner so that there may be no thrust, so that we can counteract this centripetal force. Okay, so now what are we going to do with this information that we've been given? We need to sum, I always say, sum forces in the x-axis and in the y-axis. All right, so what are the forces? What is the data that we have? We have the velocity has been given in kilometers per hour, but what do we do? We change it into what? Meters per second. The length of one rail to another is what? 1.5 meters. What is the radius of this circular path? 500 meters. So in our solution, all right, when we are dealing with centripetal forces, centripetal acceleration, motion in a circle, we always deal with forces. So I implore you and encourage you to always be summing forces. First, it is best to start with the y-axis because the y-axis has a ready expression of the normal force. The normal force will be very important to you, all right? When you sum forces in the y-axis, like I always say, I don't know if you can see here, we have our normal force pointing in that direction at this angle, and this angle is always equal to this angle. So this angle which we have here, if we have our normal force pointing like that, and then we have our y-axis coming like that, it is also equal to this angle. So our normal force pointing in that direction, we have normal force cos the angle, we are in the y-axis. Normal force cos the angle will give us the component of the normal force in the y-axis like that. And then we have in the y-axis pointing downward, we have the weight of the train. All right, we have not been given the mass of the train, don't worry, it will cancel out. So we have a situation whereby we have this expression. Now we use this expression in the x-axis, all right? We'll have centripetal force. Centripetal force, I'm sure you have seen that. I've drawn my centripetal force. pointing in this direction. All right, centripetal force in the positive x-axis, and then my normal force, the component of it in the x-axis, will be pointing in that direction, which is normal sine theta. The normal x will be normal sine theta. So in fact, here I just equated it. But if I wanted, I would have put a minus and put a nickel sign. But anyway, we saw how it came about and how it came about to this expression. We saw it. And then with centripetal force being given by this expression, we were able to remove where there is centripetal force, we put what? This expression. And it is this expression that we have here, so that M and M there can cancel out. From there, we can find our angle. In fact, Zoom is almost going out. So I would like you guys to go back to the link. But you just have to wait for me for 5 minutes. I want to do something, and then you come back to the meeting. So Zoom is going out in less than a minute. But yeah, you go back to the link. But I've just shown you how you are able to calculate the angle. From there, you have your tan theta, and you have your velocity, which we calculated, and we converted in meters per second. We have our radius, which was 500 meters. And then resolving this expression, we were able to find tan theta, which on the other side, we were able to use it to find the angle. So we're able to use it to find the angle. And of course, when